3.5. We may do both today, though.
I
See how chipper we feel.
I just won't take continuous.
I know you're just sucking in knowledge continuously, and then you go to college next year. You only got like 2 classes a day, and you get the rest of the day off. And by the way, I met your parents last night or yesterday afternoon. I didn't see you though.
Yeah, I don't know what I was doing. I was probably doing something.
Were your parents just there for Chase or?
I know, but they were just there to trip me.
Gotcha. He gave a really good speech. I was very impressed with him.
Also,
yes.
I got to sit in on my college math class.
I heard. Your parents told me at conferences,
They were doing some,
which was awesome because behind your parents was a line of people ready to yell at me about Dr. Buchanan. And I was like, at least one of these is going to go well for me. So, okay, let's take a peek. 3.3, we've got inverse trig functions. Real quick, what is an inverse trig function? What is an inverse trig function? Okay, so inverse. Arctangent is an example. What's the question an inverse trig function answers? What's the question an inverse trig function answers? What's that? When you want to untake the tan. So you ask yourself what angle has a sine, cosine, tangent of that value. What angle has a sine, cosine, tangent of that value? So you're inversing. Instead of plugging in pi over 6 and saying, what's the ratio of vertical to total distance? Now you're saying, okay, here's the ratio. What angle would give me that ratio? So you're inversing the question for it on that. So there's 2 things we're going to talk about in this. For number 1, we're going to prove. So notice, we did kind of do some proofs because now you're at the level of mathematical maturity. You saw this back in AB, or you saw this back in IB last year, and now you're seeing it for the second time. So we can talk about proof and then get you motivated to take advanced calculus one day. So number 1, we're going to prove the inverse function's derivative. 3.3 is I'll get there in just a second. Then number 2, we're going to go over the inverse trig derivatives. But what is 3.3? 3.3 is inverse trig functions. And then just so we don't leave any child behind, I'm going to try to get to 3.5 today. 3.5 is more than likely something everybody in your life has skipped before today, but it's hyperbolic trig functions. I'm not going to lie to you. I'm just going to tell you how to take the derivative of it. If you are interested in what they are, what they do, yes, I'm not going to spend a whole day talking about that to you today because, frankly, unless you decide to become a theoretical mathematician, they mean nothing to you. It's like teaching a whole bunch of kids in Algebra 1, like how to find the imaginary roots of a quadratic. They don't care. They just want to pass the class. And at this point in your mathematical life, if you want to learn more about that, the internet exists. Okay, real quick, what do inverse functions do to each other? What do inverse functions do to each other? Talk to the person sitting next to you real quick. What do inverse functions do to each other?
That's an
Volunteer, what do inverse functions do to each other? Like me and the person sitting next to me are inverses. What do we do to each other? You undo each other. So in other words, if f and g are inverses, what's f of g of x equal to?
1.
Not 0. No, not 1. If the derivative is equal to 1. X, right. F of g of x is equal to 1. And g of f of x is equal to? I said that wrong. I think I said that wrong. F of g of x is equal to x.
Yes.
What's g of f of x equal to? X as well. Right, they undo each other. If you remember back to honors FST, they reflect through the line y equals x. They undo each other. So in other words, f of g of x is equal to x. G of f of x is equal to x. In other words, whatever f's function is, g undoes it. So in other words, if f is like the square root of x, what would g have to be? X squared, right, because what undoes the square root? Squaring it, right. If it's e to the x, what would g have to be? ln, right, because ln undoes e. Inverses undo each other. That's a inverse functions undo each other. So, of course, it relates to relationships because, you fall for the person, you spend all your time together, you give them a sweatshirt, they give you a sweatshirt back, you give them a CD or MP3 player or whatever, they give it back, give you one back, you give them a graphing calculator for homecoming, they give you one back for Sadie's. Then you break up, and what do you have to do? You have to undo all these functions you've created with each other, which means you have to delete them from your Instagram, Facebook, and all that. You have to give them back the calculator. They give you back the one you gave. You give them back the sweatshirt. They give you back the one they do. Or you just leave them in Beckman's classroom, and magically they find them, and that undoes it for each other. And it's only awkward for Beckman that he has multiple sweatshirts sitting in here waiting for people to discover their ex is leaving it for them. But inverse functions undo each other.
That definitely has like very specific.
Oh, yes, it happened because we had multiple couples in debate last year. Beckman, it felt like needed to be a priest or a rabbi or something on the buses because, oh my goodness, we had couples whose sole goal on bus trips was to sit next to each other, violating our team rule of you don't sit next to somebody of the opposite gender. Yes.
True for me as well.
Not that I'm aware of.
No,
Is there something you want to tell me?
No.
You and Emily were on the bus trying to sit next to each other too?
Well, I might want to sit next to somebody on the bus if we go on a bus this year.
Well, it ain't gonna be Emily.
Wait a minute.
The number one rule of debate is don't change the population. And that applies to many, many, many situations that we run into. Many situations.
Created negative 1/12 per person.
All right, you can have that talk with her dad. Please record it and put it on YouTube. You weren't combining like terms. We are making negative
1/12 of a person.
That doesn't make her dad want to dig a hole. I don't know what does. That's the number one. Okay, so inverse functions undo each other. So if f and g are inverses, do noted, I will let Mrs. Smith know not to sit next because debate is where people go to find true love at the school. So if f and g are inverses, then f of g of x is equal to x, and g of f of x is also equal to x because they undo each other. Like I mentioned, if f of x is equal to the square root of x and g of x is equal to x squared, then if you plug g into f, you get x. And if you plug f into g, you get x. That's what they are. So I'm going to be a risk taker today, and we are going to prove this, even though I didn't really think about this ahead of time, but there is a trick that you have to use for this. I'm just hoping that as I start to do the proof, I will remember, in fact, myself, what the trick is. So what we want to find is the derivative of the inverse. So let g be the inverse of f. So in other words, g of f of x is equal to x. Okay, questions so far? Have I done any calculus? That was to you guys. Have I done any calculus? No. What kind of function is that? It's an inverse, but it's also a what function? Composite, which means we're going to use the what? Chain rule. So if we take the derivative of both sides. Okay, now I always say, which side is what? Which side is easier?
X equals x.
That's not there. Which side is easier? Right, yeah. What's the derivative of x? 1. That's actually one of the killer plays right there. Okay, now this is going to be a what rule? Chain rule. Okay, so we take the chain. So this is equal to g prime with f of x inside multiplied by f prime. I'm still not thinking. What is the kicker? What is the key of this one? What is the key of this one? What is the key of this one? Well, we're trying to find the derivative of the inverse. What's the inverse of f? G. I may have to come back to this one. I'm trying to think of what the inverse derivative is. Derivative of the inverse is. See, you jinxed me today. Now I was thinking I knew this one off the top of my head. Now I don't. Leave 4 lines. That's how much I need. Leave 4 lines. We'll talk about it. I got to remember what the...
Isn't the derivative of the inverse function 1 over the derivative of the regular function?
Yeah, but I'm trying to think of why that is. Give me 4 lines. Let's take a look. Let's talk about inverse trig functions. Iona, you jinxed me. Now I'm going to have to think about that. Inverse of a trig function. It answers the question. Answers the question, what angle instead of what's the sine, you instead say what angle has a sine of. What angle has a sine of? It's so elegant, too. It's so elegant. I feel like I blew math for you today. Yes?
When we say sine of something, how can we just not write the E?
I don't know. Budget cuts. I don't know. If Mohit was here right now, I would show you some of his homework from DiffyQ. And I guess on a 15-page problem, Mohit, he's in DiffyQ right now. On a 15-page problem, not having to write that E several times, I guess maybe that's what saves you from carpal tunnel, but I'm not sure that that's like actually about. The basic reason is mathematicians are really lazy and want to write as little as possible, and they probably couldn't get away with just SI, so they probably wrote the N. And then somebody asked them, why not SINE? And they're like, that's too much writing. Lazy. Which is why we invent symbols like this for therefore, because that's way less writing than therefore, but I guess sin and sine are. What's the notation for that if you don't remember? Sine inverse, cosine inverse, tangent inverse. Now, the argument in math becomes, what's the difference between arc sine, arc cosine, and sine inverse? That really depends on your math teacher. That slowly they've become the same thing, which is bad because they weren't back in the days that we had like a small number of calculators. Because the bottom line is if you plug sine inverse into your calculator, how many answers do you get out? 1, which maintains that sine inverse is then a function. Like there's only one answer it's going to give you. Are there a million? Yeah, there's a million different angles that have the sine of 1/2. But there's only one you want back from your calculator, which maintained that then sine inverse was a function. Arc sine would return all of the values. So then you put like, pi over 6 plus 2 pi n or pi over 3 plus pi n. So it would return all of the values. Arc would be all, sine inverse would be 1, but slowly they became the same thing in math, which pains my soul, but nobody cared what I was thinking, so they didn't ask me. So notation for this. Then let's also write above. Let's write what the domain of this is. And then the range of answers we're going to get out. Not really because you need to know this, but really just to remind you of like what the answers are that we're going to get out. Okay, sine inverse. What's the domain of sine inverse? Well, what's the smallest sine we could have? No. -1, right. What's the largest? 1, right, because we emphasize that over and over and over in chapter 1. The sign just kind of oscillates between -1 and 1. Why bracket, not parenthesis? Yeah, because you can actually get out -1. That means you're shooting the missile straight down. 100% of the direction is towards the vertical, but it's going down. Can you actually get 1? Yes, all of your motion is straight up. If you remember, if you're my honors FST or honors pre-calc class, I don't define it with X and Y. I define it with vertical and horizontal because that's how we use sine in the real world. Think of sine as how much vertical percentage you have. Think of cosine as how much horizontal percentage you have. So cosine then also has that same domain. Now, for it to be a function, it has to give out 1. What range did they choose? Well, they chose -pi/2 to pi/2. Because you can get every angle between -1 and 1 between -pi/2 and pi/2. What about cosine? Cosine starts at 0, though, so they started it at 0 and just went to pi. So in other words, you can plug in numbers between 1 and 1, and you'll get an answer out between 0 and pi. Cosine always gives you a positive answer. Tangent. What can you get from tangent? Well, tangent goes from where to where? Negative infinity to right, negative infinity, right. Negative infinity to infinity. Brackets or parentheses? Parentheses, because infinity is a journey, not a destination. Right, journey, not a destination. See, we're jinxing each other today. And then what do you get out from that? You could get out -pi/2 to pi over 2. Now, a Doug question on this one. Why can't you actually get pi over 2? Why is it a parenthesis, not a bracket? Yeah, because you can't actually get negative infinity. Why can't you get pi over 2? Because you can't actually get infinity. Now, several teachers would derive the rule for this. Yeah, if you want to do that, take advanced calc. I'm not going to show you the intermediate ones. I'm just going to show you the ones that involve the chain rule for these functions. Hopefully, you'll forgive me for not doing more. Yes, question.
For the domain and range, are we looking at the graphs of them or the graphs of the inverse?
Okay, when you look at the graph of the inverse, you're going to switch the what and the what. The x and the y, yes. So when you look at the domain of this, you're looking at the y values for sine. When you look at the range for this, you're looking at the input values of the domain for sine. Yeah. These are correct for sine inverse, cosine inverse, tangent. In my mind, even though it might not be in your mind, I have dreams that you knew it for sine, cosine, and tangent off the top of your head. But those are my dreams, not yours. Other questions? Other questions? Well, let's get you the rules. Why not? Sine inverse, cosine inverse. Oh, I thought that was the announcement thing. Sine inverse, cosine inverse, tangent inverse. So the derivative with respect to x of sine inverse of u is equal to 1 over the square root of 1 minus u squared times du dx.
Yeah.
She literally told us not to learn these. She gave it to us one
So
class. and
why
she's like,
did you not reply back? So why are we spending class time on it
We
then?
didn't. She just gave it the sheet to us with them on it. She was like, "You guys won't need it. It won't be on the test. It was definitely on the test."
Isn't
That
there?
was on the test.
I was gonna say I one of the, because you know how you're told not to tell anybody what's on the test, and then of course what do students do? Come back and ask you how to do questions on the test. And one of them was an arc cosine one last year, I believe.
Yep.
So yes, you do have to know these. That's why I'm covering them in class. Now, hyperbolic, do you have to understand these? No, I don't have a week to talk about hyperbolic in BC, so you're just going to memorize those. Notice I relatively took you through sine and cosine, yes. Now, how do you do that? Use the inverse one, and it's an elegant proof, and I'm mad at myself. I can't remember it now. I'll blame the humidity. Okay, next one, the derivative of inverse cosine. So I'm mad at you, Ayana. You should have came back then. If I don't have to know this, then why are they on this sheet? Which probably had a title of things like things you need to know for the AP test. You're just trying to. You're just trying to be BFFs with her, or what?
No, I was trying to hear. I don't know for everything I said, so I just stopped asking.
Okay, and I made see what happens when you talk. No, that was cosine. That was sine. Cosine has the positive. Is equal to 1 over the square root of 1 plus u squared times du dx.
All these right for the AP test.
Why not?
Yeah.
Why not?
And then they ended up being on the test. Hey.
Why not?
I didn't do that. I didn't.
Why not? And good news for you.
I got to that first trig, and I said, no, I'm not.
I made a mistake. I forgot it's not a negative, it's a positive, but the negative goes on top. Who said okay? I knew that. Good for you. Okay. I lied to you. The negative, I've tried to remember the rule for the top. The negative goes on top for cosine, it goes inside for tangent. Oopsies.
So it's still 1 minus u squared.
It's okay.
It is still 1 minus u squared. Yeah, but cosine is negative, sine is positive, just like the derivative of sine is positive. The derivative of cosine is negative. I thought the negative went in, but no, the negative goes on top. Tangent has the positive. Derivative of tangent inverse of u is equal to 1 over 1 plus u squared times du dx.
No square root.
No square root for tangent. No. No square root for tangent. Cosecant and secant have a little different theme to them. Now, which ones do you have to have memorized? These are the 3 you need to have memorized for the test, which apparently they just told you to do last year. The other 3 you just have to have for your homework tonight, but they're just basically giving you extra chain rule problems that involve these.
Sick.
Wait, so for like cotangent, would it just be 1 plus u squared minus u over dx?
For no, it's not that nice. Sorry. I wish it was, but it's not. Okay, let's look at then the inverse trig ones for secant, cosecant, cotangent. Which one should we do first? Let's do secant first. Secant. These I do not have memorized, and I don't expect you to. The derivative with respect to x of the secant inverse of u. This one, a little more complicated. 1 over u times the square root of u squared. Is it plus 1 or minus 1? I think it's minus, but I have to look it up. It's minus times du dx. It is not even in the learner descriptors. Like there's a list of things you have to know for the test. The inverse sine, cosine, tangent are. The inverse sine hyperbolic, cosine hyperbolic, tangent hyperbolic are. Secant inverse, cosecant inverse, cotangent inverse are not on there.
For the AP.
Yeah. And practical life applications.
What do they mean?
Because we can.
You can't what?
Because we can't find the secant inverse. That's the only reason why, because we can. Why? I mean, is there a practical life application? No, but I hate to break this to you. A lot of math professors in college are going to be really disappointed when something has real life applications, because that means other people can understand it besides them. Blame Chaudhary for it. Okay, next one, cosecant. It is Chaudhary's, never mind. See, you're a nicer guy than you should be. Cosecant, I think it's x squared minus 1. Nope, it's negative out in front. Negative 1 over u, square root of u squared minus 1 du dx. Notice it's backwards. The one that goes with cosine gets the positive. The one that goes with sine gets the negative. But the s gets the positive. The c gets the negative. That's how most people remember it. So then Chewy asked something about cotangent negative. Oh, Kiwi asked.
I like Chewy. Come on, that's funny.
Du dx. Cotangent has a negative up top, but the same thing on bottom. So no, it's not the reciprocal of it. Boy, it'd be nice if it was.
Who came up with this?
Our boy Newton, because that's the next section is Newton's method.
Oh, and Euler's method?
No, that's in second semester. That involves advanced integrals.
What's an advanced?
That's it. That Mr. Krabs. That Mr. Krabs.
Is that a 0?
Yeah, 0 to infinity. Or we could make it more fun. We could go from negative infinity isn't defined for that, but we could go from negative infinity to infinity. So that's, in fact, that's why Ayana, and it destroyed me last year in the class because I ended up having to teach everything about limits in the unit that had everything about integrals in it, because this ends up being a limit. They just memorized like Boba Betsy, and I let them get away with that. And then when we got to that, like there was no prayer of them getting any of these problems right. So then I had to go back and reteach all of limits to a bunch of kids who were almost ready for the AP test. And that's why I made limits a really big deal this year, because then that stuff really becomes pretty easy, because all it involves is like the limit of 1 over x squared plus the limit of 1 over ln x, and it's not that bad. But if you don't understand limits, you can't get any of those right, which last year tanked me. So this year you had to suffer. Sorry. Okay, stop and check out before we go any further. Questions on that? All I've given you so far is what? Formulas. Let's take a look. Who wants to do a question? Easy one or hard one first? Oh, let's do a chain rule one that's got a tangent in the middle. Chain rule one that's got a tangent in the middle. What should we go for? What should we go for? What should we go for? Oh, yeah, let's do one of those. Okay, so example number 1. Let's go for the tangent inverse of, I don't know, 3x. And you got to find the derivative of that puppy. Okay, you're really, really smart. What's u equal to? So what's du equal to? 3 dx. Oh, no, we don't need that yet. Not for this class yet. We'll just pretend that doesn't exist yet. Shh. Wait, I know it's coming, but it's not there yet. Okay, so u is equal to 3. Okay, so then you go, okay, well, the formula for tangent inverse is, 1 over what? U squared times derivative of u, which is just 3. So we got the top. So we got 3 over 1 plus, well, what's that squared? Okay, easy enough? Easy enough. Now, here's the harder part. You kind of have foresight because you've done this before. The hard part is going to be when we have to find the what. No. I think next, well, for you, it's this semester, but the bad part of these is when we have to find the integral. Because now you have to figure out, like, okay, this is an easy u. You can figure out, okay, u is just 3x. Now imagine u is like the square root of the quantity 1 plus x squared plus 3x. That's when it's, bless you, that's when it's really hard to go backwards with these, because then they give you the original problem, but not directly what u is equal to in the original. You kind of recognize the format that it's 1 plus something squared. Then you got to have the derivative of that something up front. That's where these are really hard, is when you have to do trig inverse integrals. That's the not that fun part. And that's where we start Calc 2, because that's a Calc 2 problem, not a Calc 1. But that's where you can't just skip over in Calc 1, because then you see the integrals that have that, and you're like, we didn't do that. And that's really actually the reason why we do this section.
Did we start integrals next?
One more chapter, optimization, related rates problems, and then integrals. So thanks, after Thanksgiving. Yep.
So is AB doing this as well?
This is AB. Yeah, but they just did the start of the chain rule today. Like I taught first chain rule lesson today. Others. So they're solid 2.5 weeks behind you. Others. All right, could you do one of those on your own? Okay, let's give you one of these. Example 2. Harder or just as hard?
Hard.
Okay, let's go for the sine of tangent inverse. No. That's too easy. The sine of cosine inverse of 3x squared plus 2, x plus 1. I know, sexy. And then I want you to think back real quick. When you get your answer, just imagine you had to take the integral of that. Just imagine you had to take the integral of that.
And you want sinus, not just sine of that, not sine inverse of that.
Correct. Sine of the cosine. Oh, we could. No. The domain range thing wouldn't work out. No. We don't want to talk about that. Kiwi, we want suffering. We don't want students to give up on life.
How much do we have to simplify this?
None. It's a free response. There's no multiple choice answers. Well, again, here's the deal. Really, why do we do this section is so when you run into the integrals, you've at least recognized, like, when I had a derivative that was this was the original function. So you can start that backwards thinking process. If you just hand kids a sheet and say, you don't have to learn this, go get them, Tiger, and then they have to do integrals based on that, that could not go well. I know firsthand because I taught this last year after I just kind of skimmed this section. Because I went, once I realized how bad things were, I went really fast. And that didn't necessarily go the best. Attendance, though. Oh, you guys aren't sitting in the same seat, so I better take it from scratch. 2, 4, 6, 8, 10. Oh, Noah, can you go get something from Mr. Bear that needs to be graded? He's in 507, and then he wrote this quiz. So if he wants to say, is there a way you want me to grade it, or do you want Beckman to figure out how to grade it? So, oh yeah, test. No, you don't have a test out. I got all your tests back, except your makeups. I am having to grade the teacher that quit stuff, so be patient, be nice. Hopefully we'll have somebody in there soon who
Be
can.
harsh. Is that what you said?
Dr. Buchanan, apparently 13 years at the academy, was able to get through 6 weeks here at DCC.
Are you serious?
Yes.
Like a heart attack.
He was gone.
Because I got
How
some.
come he was saying the department head?
What's that?
Why did
I was like the department head.
He wasn't. I've been the department head all year. I just have to deal with him quitting.
I was like, why would you make him that?
Oh, because department head is not a luxurious position. Sometimes it's determined just by who wasn't there for that meeting.
Who was the department head before you?
Kumar and Schwinghammer did it together.
Interesting. Why do they do everything together?
They were inseparable. All right, Willow's here, Cameron's here, Alexis, Caleb, Matt,
Okay.
Josh. Riley is gone. That's one.
Shampoo. Where's Riley?
Shampoo is gone. I don't know where Riley is. He didn't tell me. Shampoo is gone too. Warner, Wells, Underwood, Trelios, Blood, Practical. All right, there we go.
Jesus Christ.
Oh, Caleb.
Yes.
Stupid.
What did I do?
I'm just stupid. All right, volunteer. What rules are we going to use on this one? First off, holy math. This is a chain rule with a inverse cosine that's also going to be
In a sign.
in a sign and a chain rule to finish it off. Yeah, I mean, look at that. Go to Mod Pizza and describe that for them and tell them to make it super fast. So that's going to be a chain rule, a sine, a cosine inverse finished off by a chain rule at the end. It's going to be no fun. What do we deal with first? Volunteer. What do we deal with first? Ariana. Sine. Right. What's the derivative of sine? Okay. Cosine of the cosine inverse of 3x squared. Somebody asked about simplifying. Here's where we will simplify a little bit. Okay, so that's that. So we got the cosine of the cosine inverse. All right. Then we take the derivative of cosine inverse, which is -1 over, yep, that whole thing. Then multiplied by what? Yeah, 6x plus 2, because then you got to take the derivative of the inside of that. So 6x plus 2. Whew. Now, what do you think the part people are going to forget is? Yeah, 6x plus 2, because they feel like they've finished enough work to get this problem right, but no, you haven't yet. There's still more suffering to do. So then let's clean it up a little bit. Cosine of the cosine inverse, what do those do to each other? Yeah, basically cancel each other out. Now, that's your pre-calc teacher would beat me for saying that because they want you to have a deeper understanding. But at this point, okay. So that gives you a 3x squared.
You were our pre-calc.
Yeah, and I would beat you for saying that. Times, okay, then I got a -1 times that. So I'm going to just bring that in, -6x plus 2 over. Oh, let me rewrite that. Somebody asked a question anyway. Hold on. Shh. I can't deal with you talking. I'm not Mrs. Kumar. Mrs. Kumar's female. She can deal with people talking right at the same time. Males can't do that. So this is equal to, okay, so I got this on top, 3x squared plus 2x plus 1. I got this on top, a negative, and then a 6x plus 2. And then I got all this on the bottom, the square root of 1 minus this train wreck squared. That's as much simplifying as I would do. Now, is it possible you can FOIL this out and something good will happen? Yeah, I have a feeling like this one and this one are going to cancel each other out, but that's not really that great of an answer. Could I move the negative out front? Yeah, I could. Does it really matter where it is? No. Could I distribute the negative? Yeah. Does it make anything better? Not really. So that's a variation to that answer, but there are a lot of variations that you could put. You could just move the -1 out front of the whole thing. That's probably actually better. Can you bring the -1 into the square root? No, that's bad news bears. Bad news bears. That's a tough one. That's about as bad as, well, that's actually worse than anything that's on your homework tonight anyway, so that doesn't matter. All right. Yes, Caleb. Yeah, I got to figure it out. I'm stupid. I just
change because it has.
No, I'm dumb. It's not.
So are you going to be able to show us that today?
Yes. But I want to finish first because I don't want to go back and forth. Okay, questions on that? All right, let's go. You want another example? Or you're good to go on? Okay, let's good to go. Don't forget, everything we talked about before is still valid. You could still have like e to the tangent inverse. You could still have find the equation on the tangent line at that point. Like all of that continues on and on as we go out through the year. I have intentionally avoided talking about domain and range beyond that table because we'll talk about it when we get to the integral of that because that's where that becomes important. I don't want to spend 2 days on that. Ariana Sublime. Can you say it again? Not yet. I'll tell you Wednesday, though. All right, let's go to 3.5. 3.5 is hyperbolics. It's going to feel very similar to this. Actually, is it 3.5 or 3.6? It's 3.6. 3.6 is hyperbolics.
What's 3.5?
3.5 is Newton's method of linear approximation.
Are we doing that at all?
Yeah, that's the last section I'll do. 3.6 is hyperbolics. Okay, you may ask yourself, what is a hyperbolic function? Yeah, here's where we got to talk about this. Who made all of the rules of geometry?
Geometrics.
Pythagoras.
Euclid.
Euclid, right. No joke. Euclid wrote down the rules. Euclid wrote down the rules, and we derived, guys, I'll wait for you to stop talking. Euclid wrote down the rules, and then everything we learned about geometry was just based off that. And he only gave 6 rules. One of them was parallel lines never what? Okay, parallel lines never intersect. Okay, what's called alternate geometry, which guess what it's called? Hyperbolic. Hyperbolic geometry defines 2 parallel lines as any 2 lines that have alternate interior angles congruent. Another definition in hyperbolic geometry is lines can be curved. They just have to have a starting and an ending point. So you ready for this? Hyperbolic geometry. This is an example of 2 lines. This is an example of 2 lines. Do they intersect? Yes, but that's not the definition of hyperbolic geometry. In hyperbolic geometry, parallel lines are 2 lines that have what? Alternate interior angles are what? Congruent, right? So if that angle and that angle are congruent, these lines are parallel, which blows your mind because every set of parallel lines you've seen in your life has what?
No curve.
No
intersection.
No intersection, and the lines are what? Straight, right. Now, you may say, why didn't I do that? Well, because we follow Euclidean geometry. In fact, when you take geometry, hopefully on the first day, or they show you Donald Duck in Math Magic Land, they tell you, like, this is all based off Euclid's rules. Euclid had 6 postulates that he defined out, and everything else we learned about geometry is based on that. Like, if he gave you that alternate interior angles are congruent, you can prove the corresponding angles are congruent. You can prove that alternate exterior angles are congruent. You can prove that that same side interior angles are are supplementary to each other. But there's no reason why the universe has to be Euclid's rules. In fact, you've probably heard space is curved. Are there lines in space? Is it possible for a particle to just keep going on forever? It seems theoretical, but there are other forces like gravity or wind, magnetics, all of those that can affect where a particle goes. Hyperbolic is based off that. Now, here are the definitions of those. If y is equal to the sine hyperbolic of x. Now, this is kind of weird, but this is pronounced cinch. This is pronounced cinch. The sine hyperbolic is pronounced cinch. What is the sine hyperbolic equal to? It's equal to e to the x minus e to the negative x all over x. No, 2.
This comes from imaginary. This comes from complex analysis.
Yes, that is, its origins are in complex analysis. By the way, if you major in math in college, one of the things you do is connect like geometry to algebra to complex numbers. And some days you go home and try to explain that to your friends and you just don't have friends anymore. Yes.
Does this intersect with non-Euclidean geometry? Because it seems like
that is a question well beyond my mental comprehension. Yes, Ayana.
Explain why those lines are parallel.
Okay, so at some point, someday, somebody walked up to you and said, now, okay, you got to take off your like geometry kid hat for just a second and go to theoretical geometry. So all of the things you learned in geometry were based off this guy Euclid. Have you ever watched Donald Duck in Math Magic Land? Go to YouTube. Okay, it's an American classic. How many of you have watched it before?
Let's watch it right now.
Not happening. Which teacher showed it to you? Okay, did you take that here or somewhere else? Okay, that should be required viewing. Like on one sub-day in geometry, they should show you Donald Duck in Math Magic Land. Because what Donald Duck talks about is that the rules of geometry were just written down by this guy named Euclid. And everything that you learn in your geometry class is based off of Euclidean geometry. I'm looking for the book here real quick. I took a class in college called Theoretical Geometry. Let me see which one of these folders it's in.
So
All that class was is What could we prove true if we took each one of Euclid's 6? Yeah, here it is actually. Dr. Mark Nielsen. Just FYI, can I tell you a really good piece of advice in college? If you have a really bad professor and then that really bad professor wrote your book, guess what you are for that class? Yeah, insert your favorite nun. So Mark Nielsen taught this class. Mark Nielsen was awful, and he wrote the book for this class, so he made you buy a book that he wrote for the class. Well, guess who wrote the same explanation? So basically, what does he do in class? Copy down exactly what he wrote in his own book that you had to pay $100 for. So just FYI, if you find that on the first day of class, you need to really analyze, can I learn from this person? Because if you can't learn from them and they wrote the book, what also can't you probably learn from? The book, which means you need to find somebody smart or just pray or whatever you believe in a lot in that class to pass. Because I got a C in that class and I'm never more thankful for a C in my life. So anyways, all this class does is take everything you learned in geometry and say, well, what if we assume that parallel lines can intersect? Well, what if tomorrow we assume that triangles could have the sum of a triangle could be something besides 180, and then go back and prove everything else on this? In hyperbolic geometry, are you ready for this? You ready for your brain to explode? A right triangle can have 3 right angles. Now you say that can't happen because the sum should add to what? Now remember back to geometry. Hold on. How did you prove the angles of a triangle could add, that the angles of a triangle always have to add to 180? Like, why do they have to? What's that? Well, here's what you had to do. No, the lines are straight. Here's actually, and if your geometry teacher didn't do this, you should sue them because they should have. So here's a triangle. Okay. Can I pick on somebody?
Yes.
Sure.
Will, you look like, do you remember this proof? Okay, Will, pick one of those 3 sides. I don't care which one you pick. AB, BC, or AC. Pick one of those 3. AB. Okay, so notice this one. I'm going to draw a line parallel to AB going through the point C. I'm going to draw a line parallel to AB going through the point C. This is how you prove that every single triangle has a 180-degree sum. Okay, now you know this plus this plus this have to add to what? 180, because it's half of a 360. Now let me ask you a question. This angle is angle C. This angle and this angle are what kind? Alternate interior, right? So these are what? So this is angle 1, angle 2, angle 3. This one is also the same as angle what? 1. And this one and this one are also what kind? 3. So if 1 plus 2 plus 3 is equal to 180, this is the same as 1, this is the same as 3. That's how you prove that the sum of an angle of a triangle is equal to 180. Now that uses the properties of what? Parallel lines. If now you assume parallel lines could intersect, now triangles can have different sums than 180 degrees. In fact, in this hyperbolic geometry, which is one of the alternate geometries, you can have a triangle 3 right angles. Which you say, whoa, that'd be great. But remember, lines aren't what?
Yeah, draw it.
Straight. Okay, that's...
That was really aggressive.
That's a circle.
It's on a sphere, though.
There's also no 90 degree.
Okay, you asked, okay, I'm not very good at art, but that's what you basically do. You just draw 3 arcs at each arc at 90 degrees. They intersect, they add 270. Now you say that's not a triangle because it doesn't have what? 3 sides, because you define sides as being what? Straight lines. But if you now make lines where lines can be curved, yes, a triangle can have 2. Okay, so anyways, that goes back to, okay, way past the, Caleb, sit down. I know it. No, we're not talking about it anymore. No, we're not talking about it. No, we're not talking about it anymore. That's, people are going to go home tonight. I guarantee one of you is going to do this. You're going to go home tonight. You're like, Beckman told me 3 right angles, and your parents are going to be like, look at the quality we had. They can. It just depends on your definitions. And that goes back to, what did we start this class with? Really rigorous definitions of the things we were talking about. Kiwi.
Who wrote the alternate geometry?
It's somewhere in that book. Off the top of my head, I feel like it was an American, because that class I really hated America. Like, who had time to think of this? Like, shouldn't we have been doing something more productive with our time? But like I said, if you have a prof that's not very good, and then that prof wrote your book, you're in a lot of trouble, because then you just can't even read the book, because guess who wrote the book? And then you look at your notes and you're like, wait a minute, the notes in the book and the notes we took in the class are the same thing. And then you start talking yourself into things like, I don't really have to go to this class, I can just read the book. because it's going to be the same thing. And then you get in trouble because you don't go to class. Yeah.
So then what do you use to define the sides of the triangle?
I don't want to go any further with that. I feel like I'm already blowing your brains away. And one of you is going to go home and tell your parents, like Beckman said, a triangle could have 3 right angles. And your parents are going to be like, I knew I wanted him fired. I knew that Beckman was teaching our kids voodoo magic. Bring back Buchanan, right? He was, yeah, he wouldn't have mentioned that. All right, so here we go. So going back, the definition of sine hyperbolic is it's e to the x minus e to the negative x all over 2. It is pronounced sinh. So this is the sinh of x, the sinh of x. Hyperbolic cosine is pronounced cosh. The cosh of x. The cosh of x is e to the x plus e to the negative x over 2. Now, for the purpose of this class, do you really have to know that? No, you don't. But I want to give you at least some background on it. 99 math teachers out of 100 would have just told you what the derivatives are. Here's what the derivatives are, and I'm only going to give you 3 of them, the ones you need to know for your AP Calc test. I'm not going to go through all of them. The derivative of sine hyperbolic. The derivative of sine hyperbolic is cosine hyperbolic. The derivative of sinh is cosh. Now you say, wait a minute, the derivative of sine is negative. No, same as it was before. Derivative of sinh is cosh. The derivative of cosh. Don't you wish? No, it's just sinh. Question, how are we going to get a negative out of here? Well, then when we get that negative, we get that same thing back. When you take the derivative of that, you're going to get that negative, which returns this function back. When you take the derivative of that, you're going to get a negative, which returns it back to a positive. The derivatives are just each other for sine and cosine. And then the derivative for tangent hyperbolic, which is the last one I'm even going to bother talking about, is secant Hosh squared. Spelled it wrong. I actually don't remember how that one's pronounced. That sounds way too close to something else. But it would make it easy for you to remember. Okay, now some duck questions that I'm not even going to. No. Caleb, you already. Yes, this is all hyperbolic. Now, is hyperbolic fair game on your AP test? Yeah, well, and it was last year too. It's on the AB. You probably just looked at this and you're like, there's no H in sine. They spelled it wrong. So I'm getting your Cameron.
What is the EBX minus X? What is that?
Definition of sine hyperbolic. Sine hyperbolic is this. Cosine hyperbolic is this. That's its definition.
What was tangent hyperbolic? Not the derivative, but actual tangent.
I don't remember that one off the top of my head. Well, hold on a second. It's sine over cosine, so it would be this. Yeah, that doesn't factor. Yes, Caleb.
I figured out the inverse function there.
Yeah, I'm getting to that. As soon as I had a moment to think about it, I kicked myself for not remembering it. Josh.
So when we're writing secant hyperbolic, is it secant squared then h or secant h squared?
Secant squared and then the h, just like it is for sine and cosine. Yep.
Can you show us a problem that would actually like have this and see how it might be like worded and set up and like what it's actually asking for?
Yes. Have I ever taught you something and not done examples?
Well, but I'm just like, I don't even know what situation I would even use.
So you're in a dark alley on the AP Calculus BC test, and this comes up, and you're like, man, there's that one problem Beckman's going to tell me about, and then I can delete this from my memory forever. So example number 1. Willow, you want an easy one or a hard one? AKA, do you want one that's got this or this and the chain rule in it?
Do just this and then do the...
Okay, let's do it. Okay, so you're in a dark alley, and they ask you what's the derivative of the sine hyperbolic of x.
That's it.
Now, well, because I can't put anything else in there, and that makes it a chain rule.
No, but is that like
That's
exactly what they would say?
Yeah.
It's like,
That's it.
Well, and guys, there's too much talking. She said no chain rule, which really limits like the kind of problem I could do.
well, I was thinking more like where, like, would they give like a word problem?
Oh God, no, they wouldn't give it no word problems.
Like,
No.
what sort of a?
So
It would just be like cinch that.
Yeah, it would just be find the derivative of this. Yeah. Same with, so they may put it in a free response one where you had, this is part A, you had to like find the derivative of that, and then there's a totally unrelated question for that. But there are things that you have to know and understand. These are ones you just have to memorize and kick out. That's, in fact, why Schwinghammer did that. The only reason I'm not doing that is because we will find the integral of sine inverse, cosine inverse, tangent inverse this year, which is why I want you to have practiced finding some derivatives of it. Otherwise, I'd just say memorize it. This one, it is very possible that you will have to find the derivative of this and the integral of this, but that's as far as it'll go with this. These ones aren't that bad to take the integral of because they don't really look that different than other types of problems. What are they used for in real life? You're in a dark alley and your teacher says, let's take some alternate geometry problems out. And then you realize, drop the class.
Can you put it in the?
Okay, so real quick, find that. Now this one's different because it has a what in it? Chain rule, which means you have to take the derivative of sine hyperbolic and then you have to take the derivative of the inside as well. You have to take the derivative of sine hyperbolic, then you have to take the derivative of the inside as well. On your marks, get set.
So it's like a chain.
Yes, it is. Yes, it is a chain rule.
Okay.
She initially said no chain rule problem, which really limits it because then it's just basically regurgitating the definition again.
Well, I thought it was gonna be a little more
Did you mean
complicated
for
than
it to work out?
that's the answer.
Because I put an x squared in there, so the 2 is going to cancel when it comes down. So here's how preschool works. My daughter's preschool is having a pumpkin carving contest tomorrow. However, there's a kid in the class who's allergic to pumpkins. So they're just wanting the kids to take a picture with their pumpkins. Yeah, like I can't think about Photoshop too. Yep.
Is there a way to do this on the calculator?
We'll see. I assume sine. Oh yeah, we'll do that. Yeah, there is sine. If you hit that trig button, sine hyperbolic, cosine hyperbolic, all those are in there. Yes, Cam.
Could I Photoshop your daughter next to like a 2-story tall pumpkin?
I feel like I just got a reason to give you more homework.
Gee, thanks, man.
All right, derivative of this. What's it equal to? What's the derivative of sine hyperbolic? Cosine hyperbolic. What's the derivative of 2x squared plus 1? Where's that 2x going to go? Now, some of you may have said, well, I'm going to plug that into the e to the x so that can cancel. You don't need to. This is as far as you need to go. This is as far as you need to go. So what's in this section? Basically some chain rule problems that have sine hyperbolic, cosine hyperbolic, tangent hyperbolic in them.
So you don't have to plug your back in.
Correct. Yep. Now, in the section, you're going to, so when you look at the homework, don't flip out with the problems I don't assign. This book goes further than the AP test does, but I'm not going to go further than they do because they do actually take the derivative like sine hyperbolic inverse, cosine hyperbolic inverse, tan hyperbolic inverse. I feel like this is enough. Questions on that one? Why is it a chain rule problem? Yeah. Why is this a chain rule problem? Yeah, it's composed of another function. What's the other function? X squared plus 1. All right, whip out your calculator. Go to calculate. Go to menu. What class are we in? So we're going to take the derivative. I assume it can do it. I haven't tried this yet. Go to trig. Go to, yes, look at that. There's got to type it in manually. Okay, so let's type in sinh. S-I-N-H.
If you press the little button that looks like a book right under delete.
Yep.
You can scroll down to the trigonometry. I just sound so good.
Okay. I think it'd be easier to just type it in at that point, though. Okay. Okay, so sine hyperbolic of, what did we just have? X squared plus 1? Which, oh my goodness, that looks so familiar.
I have another question. This is off topic.
Yep.
But when will, on our calculators, when will we ever use gradients?
To Calc 3.
Thank God.
So
This is Calc 1. We'll finish Calc 2 by the end of the year. The gradient's in Calc 3, and then it comes again in linear algebra.
So we're going to use radians like all years.
Gradients?
Radians.
Oh, radiant. Did you say radians in the first one?
No, I said
Okay.
gradients in the first
Okay,
one.
that's what I thought. I was like, maybe I just made up the word gradients because I wanted to talk about it. Gradients is in Calc 3 and then comes back again in linear algebra and comes back again in diffie-q. Radians, your days of degrees are over. Sorry.
Unless you're in AP physics.
Yeah, AP physics.
And you switch back and forth and it's a pain.
Yeah.
Yes, it is. And that's one of the reasons that we as mathematicians went away from that because then it's just everything's in terms of pi and everything's radians and we never have to switch back and forth. And frankly, in doing stuff by hand, it might be easier to do it with radians than it is with degrees anyways. So Anna,
This class is Calc 2 and 3.
we're not in Calc 2 yet. It depends on where you go. If you go to the Air Force Academy, they're different because they only have class 3 days a week and just for like 40 minutes. Like when I went to college, I had Calc every single day for 50 minutes. That was my Calc 1 class. So my Calc 1 class was 5 credits. At the Academy, it's only 3 credits. So it just depends on how many credits they give you. Like we will be finished with everything they cover in Calc 2 at the Academy, and we will do some more. So some of the stuff they do in Calc 3, like in fact, ironic story, Dr. Buchanan, if you don't know, he also taught math at the Academy. He taught Calc 1 and Calc 2. His son grew they don't cover that till Calc 3. So he was telling his son, like, oh, this isn't in Calc 2, you don't need it. And then he just wasn't a class he taught. It is in Calc 3. But that largely depends on where you go to college. It's why some of you will go to college. You'll get credit for Calc 1, 2, 3 for getting a 5 on the BC test. Some of you will only get credit for Calc 1, and then you'll take Calc 2. Some of, like most of the semester will be a review, but some of the stuff will be new. So they only give you credit for part of Calc 2, so you got to take it again. But it just depends on where you go to college. I mean, like Kyle Clancy went to the Academy this year, and he is taking, Ryan Clancy. Sorry. Talking to mom at conferences, Calc 2 for him there is really easy because everything in the class he's seen before.
So
Yep.
we are covering Calc 2.
It depends on where you go to college. Like,
so there's not a specific curriculum for each.
no, God did not, or I shouldn't say God. Math did not come down one day and say, thou shalt teach in Calc 1 these topics,
So
no
like
more than
the
yes.
other math.
Right. It's like if you transfer to another high school, like what they cover in Algebra 2 may be different than what we cover. Same in colleges. It just depends on what kind of college you go to. Colorado College is a good example. What's different about Colorado College than basically every other college in the universe?
You do one subject.
You do one class at a time. So when you take Calc, you can take Calc for 4 hours every day for a month. Or like if you're in physics, you take physics for 4 hours every day for a month, which is great to like delve really deep into topics, but bad because then you might not have math again for a year and a half because you only take one class at a time at CC. It's why athletes love to go to CC because if you're gone for a road trip, you only miss one class. That's the only class you're in.
So they take.
It's why their hockey program over the years has been very good because hockey players miss a lot of time because like CC went to New Hampshire last weekend. They were home this weekend. They went to Vermont the weekend before that because a lot of hockey teams are like in the corners of the country. So that's why CC was a good place for them to go to college because you only miss one class. Okay, I got 2 problems for you to do, and then I'll give you some time to work on homework. Cam.
What does cinch look like? Like how many units? What that look like?
I don't understand what the issue.
Let's
Okay,
draft.
I need those of you that are not going to get this, and this is going to like bother you to just ignore the next 15, 20 seconds. Why do you guys ask questions that like involve higher level math class? Okay, so there's some angle.
You introduced.
Okay, so you know how there's a sine, a cosine, and a tangent. You could break this up into a, guys, okay, I'm not smart enough to do this with you talking for sure. So there's a x, this is a y distance, there's an x distance, and then there's a radius. With me so far? So sine, cosine, tangent are the ratio of like this to this, this to this, this to this. Okay, but notice there's this area over here. Makes a hyperbolic. This area is what like sine, cosine, tangent, hyperbolic are looking at. They're looking at the ratio of this area to this area, this area to this area, this area to this area. So you can imagine as this angle gets smaller, this, what do I want to do here? No, it would be this distance right here. So we're looking at this area right here compared to this area right here. So it's looking at that residual part of the graph that's not included in the right triangle that you make and looking at the ratio of that to this as x varies, y values, as x varies, as y varies, and as the ratio from x to y varies. Now, what are the applications of that? It turns out that residual actually has some applications in ordinary differential equations. Do I remember those off the top of my head? No, but I remember my prof telling me, well, this is the reason you had to know sine hyperbolic. And I'm like, what's sine hyperbolic again? Like, I remember that day we covered it in Calc 1, and I remember not ever talking about it since that day in Calc 1. So, and then he defines that it's weird that, like, this residual has something to do with E. Like I've told you, like Like remember how this is equal to e to the x minus e to the negative x over 2? Like that's what sine hyperbolic is equal to. Isn't it weird how the distance that you have, like the distance you rotate, gives you a right triangle, and the residual of that right triangle to the unit circle, that area has a relationship with e? Like where did that come from? Like it's so weird. Like you take this class called differential equations, and like basically everything in nature is related to e. And then you think like, why is it related to e? Because we'll define e in Calc 2. We'll give a series of sequences definition for e. And then you're like, whoever invented the universe, like e is their number. Like they like pi a little bit, but e is their number because it's all over the place. And like in random places you'd never expect it to be. But anyways, that's way beyond the content of this class. If that interests you, go be a math major in college, and then you can talk about this over and over again, and then you try to go on a date with somebody who's not a math major, and they're like, they sound like they're either going to be really rich or crazy. Do I want to take a gamble on which one of the two it's going to be? So either really rich or totally crazy, like beautiful mind nuts. Which one of the two will it be? Yes, Caleb.
Yeah, so isn't all the E stuff, really a lot of this stuff in trig, come from EI theta?
Yes.
Oh, yeah.
But e to the I theta is the really easy way to take derivatives of it, because what's the derivative of e to some power?
E to some power.
Yeah, that's just really convenient that works out a lot. But anyway, in any case, okay, 2 examples, then I'll give you your homework. Example, what is this? 5 and 6. I don't know why I have 1 up there. Example 5 and 6. And then I'll finish my proof because I was 1 step away, but I wasn't confident in my step, so I didn't do it because I didn't want to be wrong. Okay, example 5. Let's take a look at the sine inverse of the natural log of 2x plus 1. Ooh, that looks really fun. And then let's go for the tangent hyperbolic of, oh yeah, find the derivative, haha, find the derivative, haha. What did I have planned for this one? Yes, yes, yes. On your marks, get set, math.
That's a natural log of 2x plus 1.
Yes, sir. I don't think, I mean, it's in the book, but I don't think they're going to cover it because you could imagine, like how many of you are totally lost on what hyperbolic is and how it relates to my life? How many of you totally get it? I can't wait to tell my parents about it tonight. Yeah, exactly. That's why they skip it in pre-calc, basically, always. Whoa. Yep. Desmos does everything.
Well, except
What doesn't Desmos do?
some things. Can't do infinite series. Can only do finite
True.
series.
It can only do finite series.
And then eventually you start plugging in bigger and bigger numbers on the series and it just freezes.
Is that 3x or 2x?
2x.
2x plus 1.
2x.
Also, back my notes supposed to be example 4 and 5.
Thanks, Kiwi.
I did half of it. No, I did. I put half of it.
Oh, wait, I can't throw this out. That's a sick. You're on.
Yeah.
Wait,
That's
What you got?
what's the other side? So, like I insight.
Yeah, I like how you have college.
Just need to chase them on.
So, the square root of 5.
There's no way you can get it. So I don't know what to
All right, the derivative of the sine inverse is equal to what?
1 over square root of 1 minus.
All right, so 1 over. So we start this puppy up. This is a, what do we got to do in this one? It's a chain rule with a log and another chain rule with a sine inverse, right? With the well, that is true. There's another, and then there's one more chain rule with the power rule, but it looks really easy because it's just going to end up being a constant. So, ready, set, let's go. First thing we have to deal with is what? Sine inverse. What's the derivative of sine inverse again? Okay, so u is equal to that train wreck, so ln of 2x plus 1 squared. Then multiply that by what? Okay, what's the derivative of the ln? Okay, are we done? No, we're not actually. Because remember, all of this is just for the ln. All of that's just for the ln. So we need to then take the derivative of that, which is, hold on just a sec. No. We are done. That's it. That's it. Yeah, that's it. Okay, clean it up a little bit. We can move this 2x plus 1 out front. We can move the 2 on top. So 2 over, guys, don't talk when I'm talking, please. Square root of 1 minus ln of 2x plus 1, the entire quantity squared. All right, stop and check up. Questions on that? Okay, derivative of a tangent hyperbolic is what?
Secant squared.
Okay, so we have secant h squared.
Wait, I thought you said
Oh.
secant squared h.
There you go.
Actually, I'm going to have to look that one up. I don't know what that is off the top of my head. I'm going to have to look that one up.
Put it just right over the h.
Well, let's do this. Let's do that. Now we're safe. Now we need to multiply that by what?
The derivative of
8x, yeah, which is the derivative of 4x squared. Actually, my natural inclination is to put it there, but I'm going to have to look that one up. Okay, let me go back and finish up. So apparently I don't pull another teacher here. Go back to the 4 lines I needed for you. 4 lines I needed from you. I'm going to show you why I didn't recognize it and hope that it helps you to why you can recognize it without being seen. Okay, I had this in terms of g of f. I'm going to put it all in terms of f. F inverse of f. If you plug the function into the inverse, what does it give you? X. Okay, now I want to find the derivative of that. So I want to take the derivative with respect to both sides. Let's do the easy part first. What's the derivative of x equal to? 1. Notice I moved it over. What's the derivative of the inverse? I don't know. That's what we're trying to figure out. What's the derivative of the inverse? I don't know. We're trying to do what? Figure that out, which is why I didn't recognize this in this problem because I used g instead of f. So we don't know what the derivative of the inverse is, but boy, we'd sure like to know it, aka we'd sure like to solve for it. So whatever it is, boy, we'd like to solve for it. But then we got to multiply by what? Yeah, the derivative of the inside. This is what I want to know. How do I solve for that? Divide both sides by? So here's the weird part. Caleb said this and I hushed him because I wanted it to come up later. The derivative of the inverse, we don't know. But what's it equal to? 1 over the derivative of the function. So kind of weird. If you want to know what the derivative of the inverse is, that's equal to 1 over the derivative of the function.
This is it.
That's how all of those sine inverse, cosine inverse, tangent inverse got. Because if you remember back to the glory days of the unit circle, this is equal to 1. This triangle is x squared plus y squared. If we're trying to find the inverse of something, we're trying to solve for y, we would just have 1 over the square root of x squared and 1 minus x squared. How do we find the derivative of that inverse? Just 1 over its derivative. Yes, Caleb.
It's not 1 over the derivative.
What's that?
It's not 1 over
Yeah, it is.
the derivative.
It's proven.
It's f prime, I got it down here. It's f prime of f inverse of x. 1 over f prime of f inverse of x.
No.
I looked it up.
Show it to me.
Okay.
Okay, other questions on that?
The derivative of the inverse?
What's that?
Is
The
he
derivative
saying-
of the inverse is 1 over the derivative of the function.
No, but what he just said was the derivative of the inverse is 1 over the derivative of the inverse. Is that what he just said? That's what
The
he-
derivative of the inverse with the function inside.
See,
He
that's-
just solved for the
no,
wrong
I'm
thing.
just- Like, I'm trying to point that out. Because, like, how can we find that if we don't know that inverse says it?
I'm gonna.
This will be my lunch conversation. Okay, questions on that? All right, I do have some of you, I still have your test to get back to you because I collected them back before some people took it, so I need to get it back to you today. But let's give you some brief homework on this. Then we have one more, it's just linear approximations. You've been doing linear approximations every time you found the tangent line. Newton has a small method that's a shortcut he gave. And then again, that connects to when I'll talk about Euler's method next semester. But the homework's brief tonight. There's not much of it. 3.3. Which fun ones did I pick for you? I picked on page 245. I picked 17 through 29, the odds.
Are you going to send it out?
Yep.
Okay.
And then on page 246, and you can see it's brief. There's only one page of homework in this one. 246. 1, 2, 8. Then we skip to 3.6. Hyperbolics. Page. Are you okay?
I'm good.
1, 2,
272, 25, 26, 33, 35, 43. So there's only 5 of them. And then there are no AP questions in that section.
You apparently proved it.
Now, kind of the weird thing, the AP problems end up looking like those because they basically just want to know your teacher taught you this at some point, even though there wouldn't be like a free response one that this was a part of it, but yay, there we go. So I know it's rare. Usually I teach you to understand everything, and I kind of tried to dance around understanding today, but that's what you got to do for today.
Mr. Beck, look, the humidity went up.
Yeah, when you put it right underneath there, put it back over there. It's still at 10%. That poor humidifier can't even keep up.